In this video, we're going to talk in detail about covalent bonding, what it really means, how we show it, how we figure out how many electrons are being shared, where they're being shared, and all those crazy details. So first of all, covalent bonds. We're talking about nonmetal bonding to a nonmetal. This is not going to involve any metals whatsoever. In covalent bonds that involve the nonmetals, both nonmetals tend to have a fairly strong or fairly high electronegativity. So neither one of them wants to lose. They are somehow going to share. So that's the first thing to remember, is there's going to be some sharing involved. The second thing, whenever we have a chemical that has covalent bonds in it, we're going to call that structure a molecule. Very important that we use these terms correctly. So covalent bonds, sharing of electrons from nonmetals, and the structure that they make is what we call a molecule. For example, water. What do we sometimes say? It's a water molecule. Again, we say the word molecule because it's a covalent structure. Some background stuff before we actually get going here. When they bond, how far apart are they? How close are they? How easy are they to break? How hard are they to break? And those types of things. Well, they go through that kind of first section or that second section and talk a little bit about the types of bonds and the length and the distance and those types of things. They also show on page 182 some bond strengths and bond lengths. So again, that's some good information. When we get into actual structures, we'll talk about this more in detail, but real simple. The bond length, by definition, is the distance between the two atoms. Okay, how far apart are they to share? Well, if they're big atoms and they're sharing, they'll be a little bit farther apart than if they're small atoms. Bond energy. How much energy is needed to break those bonds? Is it a really, really strong bond, which means those electrons are being shared a lot? Or is it a fairly weak bond, which means it's easy to separate one atom from the electrons compared to the other? The other thing you can notice on that chart, real simply by looking at it, the shorter the bond length, the higher the bond energy. The closer the atoms are, the harder it is to break them apart. The farther apart the atoms are, the easier it is to break them apart. Again, we'll talk about that in more detail as we look at specific structures after we've drawn them. But again, you can be familiar a little bit with that chart on page 182. All right, a couple things here to remember. Octet rule. That's come up last couple chapters. Well, I guess chapter 4 really. What is octet rule? Just think of it as 8, the magic number 8. For something to be stable, it wants to have its valence shell or its valence level full. So what's the valence level? Well, 8 electrons is the valence level. That's how many electrons it can hold. What makes that or what determines that? It's S2P6. For an atom to be stable in a chemical, it wants to somehow have the arrangement of S2P6 in its outermost shell. The only exception to that rule is going to be helium and hydrogen. They're only ever going to want one S2 to be filled. And actually helium, noble gas, is already one S2. It really doesn't even bond to anything else because it's already stable. If we go to neon, which is right below it, neon is 1s2, 2s2, 2p6. It's already s2p6. Again, doesn't want to react with anything, doesn't want to bond anything. That's the number one priority of noble gases. They are the most unreactive elements. So they're already the octet rule by themselves. All right, so we're going to start looking at um, atoms and how they're going to bond together. The two things we're going to look at, we're going to look at orbital notation, and then we're also going to look at the electron dot notation. Both of these can help us determine how many electrons are being shared and which ones are being shared. So you might have to, if you need to, you brush up a little bit of some chapter 4 stuff. All right, last thing. It'll get kind of messy when we draw the electron dots and the orbital notation. So we're going to, right off the bat, show the cleaner way to write these. And it's what we call Lewis structures. Now, they don't actually introduce Lewis structures until later in the chapter, but we really need to do it now because I know you guys, I don't want to write all the messy formulas, so I'm going to kind of open this up right now, and we'll talk about it here. So the Lewis structure is eventually going to help us to determine the 3D arrangement of the atoms as they form that molecule. A couple things that are in a Lewis structure. First of all, we obviously have to be able to write the symbols correctly. We have to start out with the correct number of electron dots. And then what we're going to do is once we decide that how many electrons are being shared, we're going to have all these arrows and it's going to be a mess. So we're going to clean up. Here's how we're going to clean up. We're just simply going to draw a line between the atoms and the symbols. And if we draw one line, we're basically saying 2 electrons are being shared between those 2 atoms, or 1 pair. If we draw 2 lines, then we basically mean 4 electrons, or 2 pairs. Okay? And if we draw 3 lines, it represents 3 pairs. So we're talking about drawing 1, 2, or 3 lines to represent a single bond, a double bond, or a triple bond. And the last thing, we want to show any unshared electrons. Any electrons that were left over that did not get used up in the bonding. When we actually look at these, you probably, hopefully this looks a little bit familiar. You know, you got exposed to it a little bit in physical science, so it's hopefully not too big of a deal. All right, so here's how you double check then the Lewis structures. This just makes sure that what you're drawing is good and you don't have to worry about any issues. First of all, when you count up your electron dots, okay, if we're doing that way, the number of electrons you start with has to equal the number of electrons that are in your final drawing. If they're not equal, then you got an issue. Number 2, don't forget the octet rule. Every element is going to have, or every atom is going to have 8 electrons around it somehow, some way. Any combination of shared or unshared electrons, totaling 8. Again, the exception being hydrogen, helium, it's only ever going to have 2. So, draw the electron dots, draw the arrows for the orbital notation, and we can start to figure out how atoms are actually going to bond together. And we got a couple ways to kind of double check to make sure what we got's right. So, let's start off here, something simple. 2 fluorine atoms. Let's say we actually wanted to bond 2 fluorine atoms together. The first thing we're going to do is we're going to draw their electron dot and see how they bond together. So, if you're doing this, first thing you want to do is draw the electron dot notation for 2 fluorine atoms. When you do this, and you'll get more comfortable in terms of maybe being more efficient and neater, I would always try and write them, close to each other, so that as we kind of draw arrows, we can kind of show what's happening with the electrons. So each fluorine atom has 7 electrons. Now, when we do the dots, you do not have to do this, but this can be a useful piece of information. You can also draw an open circle because fluorine, okay, 1s2, 2s2, 2p5, it has 7 electrons in its outermost level, but it wants to be a p6, so it's got room for 1 more. So you have to show the 7 dots if you want to show the open circle to remind you that, oh, hey, there's room for 1 more, then that's a good thing to do because it can help you figure out this answer. All right, so how do 2 fluorine atoms actually bond together? Well, what happens is it's a sharing effect. So 1 fluorine atom will actually share 1 electron, 1 to the other fluorine atom, if that second fluorine atom shares back. So what we've just shown here is each fluorine atom has 7 electrons, but by sharing 1 to the other atom, it gives the other atom 8. So really what we have at one point, they could each have 7. Another point, one could have 8, the other could have 6. Another point, one could have 6 and the other could have 8. And they're sharing those electrons back and forth. Remember, these electrons are not stationary. They're always changing. But what happens is these 2 atoms they both want an extra electron. So they're very willing to share an electron with another atom if at some point they can have 8 electrons around it. So that's our simple structure. That's literally all we do. Now, make sure that you show these as a double arrow because it does not mean the electron is leaving one atom and going to the other and never coming back. It is a two-way street. The electrons are leaving one, going to the other, and back and forth. Now, let's say we write the Lewis structure. Well, let's go back here to what we said. we draw one line between the atoms that represent a single bond if two electrons are being shared. So, the fluorine atom. There were two fluorine atoms. I draw write their symbols. Between them, I draw one line. And that one line is telling us that there are two electrons being shared between the two atoms. Then, we show the number of electrons that are not being shared. Well, if we notice here, the fluorine atom has 6 electrons that it's not sharing with the other fluorine. So those are unshared. It's important that we write those. Now, where do we put the dots? Well, remember, there's always 4 sides to a symbol. So if we imagine that the one side here of the fluorine is taken up, that means we have the other 3 sides. So what we do is we sort of rearrange the dots. And this would be the Lewis structure for a fluorine atom. As you get better at this, are you going to necessarily have to write out all these arrows and do all this? And can I just kind of do it in my head and then get to the final answer? Yeah, I'd say you can do that as long as you get the right answer. Okay. But that's what we want. That is the structure of a fluorine molecule, and we'll talk more about shapes and things like that a little bit later. Now let's say we do the orbital notation. So here's how we do the orbital notation. We actually take 2 fluorine atoms, and we're going to write out their orbital notation. Fluorine's a 2p5. Again, if you got to brush up a little bit on some chapter 4 stuff, then you'll need to do that. Okay, so there's 2 fluorine atoms. They're both a p5. In the back of our minds, we want to remember that each fluorine atom has room for 1 more electron. So now we can show, using orbital notation, what's happening. This electron will share that open spot if this electron shares back. You're going to hear me say the phrase a lot, has one, needs one. And that's the best way to show how electrons get shared. In the electron dot notation, we did that right up here. Has one, needs one. We did that down here in the orbital notation. Has one, needs one. So what the electron dots tell us, it just tells us that there are 2 being shared. Orbital notation tells us a little bit more detail. It tells us that it's 2 electrons that are in the 2p orbitals that are sharing. Okay. Which one are we going to use more? Probably in the end we're going to do the electron dot more, which is good because it's a little bit less writing. Okay. All right, so what I want to do is I want to show you just a couple more here, and then kind of take a break and move on. So we already did the orbital notation, so we're good there. All right, so let's look at oxygen. What I'm going to have you do is I want you to go through and write these down. Have you pause me, and then we'll go through and kind of show you the answer, and then if there's any questions we can talk about this some more in class. So if you want to, go ahead and pause it and draw the electron dots for oxygen, draw the orbital notation for oxygen, and then see if we can figure out the puzzle in terms of how the electrons are being shared. All right, so here's what you should have for oxygen. If you do the electron dots first, you're going to notice that oxygen has 2 spots where it has one and needs one. So what ends up happening is it shares back and forth twice. There's one time and there's a second time. So it's 2 pairs. So our final Lewis structure would start out like that. 2 pairs are being shared between the oxygen atoms. If we count carefully then, we'll notice that each oxygen has 4 electrons, or 2 pairs that were never shared. And what we do there is we just put them on the other side of the symbol. Kind of the traditional way to do it is to always put them on opposite. If there's two pairs, put them on opposite sides. Now, if we come over here to the orbital notation, we can see again, it's two pairs are being shared, and we know a little bit more detail. We know that they're being shared in the 2p orbital. Again, we notice here, try to draw them as simple as possible in terms of where the electrons are going. You may have to move them wherever, but try not, just for your visual efficiency or whatever, that you try not to cross lines too much. You can see there, I just went, straight up and straight down, straight up and straight down, shared back, and each one has a total of 8 electrons around it at any given time. Some people think this is really easy because it is kind of like a puzzle. You find a place where there's an opening, you find a place where there's an extra electron, and you try and fit the two together. And sometimes you have to fit them together only once, sometimes you have to fit them together twice. All right, last one here I'm going to have you do is water. So now when you start to have more than 2 atoms, you've got to find what's in the center. Because what we're going to find out is we never get 3 atoms that form a triangle, and we never get atoms that form a square. It's not until we get 5 atoms that we can actually form a ring or a pentagon. So whenever we have 3 atoms or 4, there has to be some type of a chain effect. So you've got to then know, well, what element is in the center? Well, in this case, I'm telling you that oxygen is the center atom. And you already know probably how to draw water's molecule, but we'll just do it anyway. So oxygen is in the center. The hydrogens are surrounding that, which means somehow the hydrogens have to connect, okay, to the oxygen. The hydrogens do not connect to each other. So I have you draw their electron dots, draw the orbital notation, and see if you can figure out how to do that. And again, pause here. We'll come back and we'll look at what the answers would be. All right, so electron dot. Again, try not to cross the arrows too much. You've got 2 spots where hydrogen has or oxygen has one and needs one. And you've got 2 hydrogens that has one, needs one. You just fit the 2 pieces together. So what we have here is 2 single bonds. Okay, just be careful. It's not a double bond, it's 2 single. So if we draw the final Lewis structure, we have a hydrogen single bonded to the oxygen, single bonded to the other oxygen. The oxygen then has 2 pairs of electrons that it does not share with those hydrogen atoms. So we draw their diagram. Now, some of you might think, wait a second, I always see water kind of like drawn bent. Hold on to that thought until section 5. Right now, we're drawing it straight. You come over here, now you can recognize that what electrons are being shared. Well, the 1s electron from hydrogen is sharing with a 2p from oxygen. A 1s from the hydrogen is sharing with a 2p from oxygen. Is that possible? Sure, because electrons can go anywhere. So we're not always going to be a 1s sharing with a 1s or a 2p sharing with a 2p. They can come from any orbital. Remember, we're talking about the probable location of electrons. So this isn't going to be a nice, neat, perfect picture of exactly, is that electron 10 or electron 11? We're keeping it pretty general. Last thing I'm going to have you do, H2S and CO2. What I want you to do is work on these on your own and show me in class. When you get to this point, be able to show me that what you've got, and as we're doing these, if you have any questions, we can look at them and do some more examples. So after you've watched the video, you're to this point, get these 2, and then in class at some point, show me what you've got in your notes. And there'll be a part 2 to section 2 just to kind of look at a little bit more complicated structures.